Okay, so it's a pleasure for me to announce Thomas Hühn from the Hochschule Nordhausen and the Evernet EG, and also Julius Schulz-Zander from the Fraunhofer HHI in Berlin, who will jointly talk about the theory and practice of Wi-Fi network development. Welcome here.
Thank you, Jannis. I'm Thomas from the Hochschule Nordhausen, and I'm a systems researcher on wireless networks. And on the other hand, there is Julius.
Yeah, also welcome from my side. Hello. I'm a senior researcher at the Fraunhofer Heinrich Hertz Institute in Berlin. I'm leading the Intelligent Network Architectures group there since early last year.
Okay. And that's our outline. So we would like to present our wireless perspective on the research we do on real wireless networks. While we have encountered over the years the gap between theory and our real systems research, followed by what we think is a major showstopper in proper systems research and looking to get things open to look into it. We will present you some challenges and potentials that we face in the work we do and make up the bridge to quantum communication, where we are quite new to, where we are at the moment not the expert, but we hope and think that once that, let's say, new technology gets into the network stack that we all use on current internet data. So all slides, so we try this the first time, all slides that start with a blue letter are taken by me, and all slides that have a purple letter are taken by Julius. So wireless everywhere. Over the last years, I think everybody has built its own Wi-Fi network at home in an unlicensed spectrum, and also has an increased coverage with its mobile phone across the country. So wireless networks are increasing quite much. That's not new. But they are totally different objectives and managements. If you look at those central and decentralized deployments. And once that wireless access technology got affordable and we got this ISM as free spectrum to use, that was like the key part to make those Wi-Fi networks a success story, and they have like a penetration all over the world. So since then, we as a systems researchers focus actually on those wireless broadband networks, typically with off-the-shelf hardware, so with your Wi-Fi chip that is around. And most of our work relies on the openness of software and hardware to have certain research done here.
Yeah, so it's not purple, it's green letter. So obviously, I mean, when we started many years ago, I mean, when we look back into the early 2000s, so most of the research that we saw in the scope of Wi-Fi network research was basically simulated or was simulated based. Yeah. So what people did was like to deploy or to evaluate new routing protocols in different simulation environments, such as, for example, NS2, OpNet, OmNet++, and these kinds of things. And they also try to evaluate, for example, different medium access schemes, for example, in the scope of the distributed coordination function and different schemes along that. and also different topologies. However, this was quite limited, and we've seen that we actually had to move into practice in order to get real results, because it turned out that the simulation-based results did not hold in the real world.
And in the following mid-2000s, real Wi-Fi systems appeared. And that's where first test beds became available, where certain setups with Wi-Fi routers, with real interference patterns happened. So that was like the entrance to look at those simulated results on real hardware with increasing channel usage. I think everybody knows a kind of Berlin backyard scenario where you have multiple access point arounds, and different standards, quite fast involved, and all rely on those DCF functions, multiple antenna systems, and those more or less uncoordinated deployments, those test beds, enabled us to try to look at those simulation results. And it turned out that a couple of them did not hold on practical devices. So lots of questions came up about those simulated results, and why is it not possible to replay them on a real Wi-Fi system. And some important aspects to this are the real system limitations. For instance, in Wi-Fi, there are a lot of non-linearities for your transmitter amplification, for your receiver amplification, and that depends on the chip you use. You don't have that, you might have the wish, but you don't get on each Wi-Fi system a channel state information. But it's all based on that simple acknowledgement kind of scheme. And a third problem that is like every time around we do this systems research is that we have to deal with closed source drivers, with unknown operation points. If you cannot fully look into the system you have on your desk. So what is that gap, if I should summarize this, between theory and practice in the Wi-Fi world? It's, yes, wrong assumptions. And if you don't have the actual system, sure, you cannot simulate it. And in a simulation, you have to assume certain things to get your work done. But the unknown system parameters, the limitations of a real hardware, let's say, they built our systems research field. So we have like real experiments on that shared medium to set up certain interference scenarios with all those multi-dependencies that we try in an experimental way to, let's say, close that gap and validate and analyze what the theory provided and what out of that holds in practice.
Yeah, and obviously, since we have to move basically from theory to practice and have to test these things in the field, there's basically the limitation when it comes to open versus closed systems. And one thing that we face all the time is that when we want to do like field testing, when we want to try out these things on real hardware, that all of these systems, basically the chips and the software that comes from the vendors, that we rely on their openness. Yeah? So we have the problem that most of these things that are basically within a router, that there are lots of small black boxes. And the problem is when we have these black boxes, we can only guess what's happening inside. Yeah? And that needs a lot of reverse engineering. So usually when we basically have a new device, we have to understand first how it works, how the inner workings are. And after that, we can actually conclude, I mean, what it might do. And that's sometimes also leads to false assumptions, yeah, and to false results. And this is clearly a big issue when it comes to research and to make a valid point and basically to publish the results with a meaningful and basically also in a comparable way, because sometimes if the components get updated, then sometimes the results are not comparable anymore. And when we now look at the inner workings and all these small submodules, they come from not just one vendor, so it's a multi-vendor environment. So we have clearly the problem that the software comes from one hand and the hardware comes out of another hand. And if you put these things together, then we are looking at this huge, basically, zoo of different components, and that's a big challenge here. So there's obviously one way, I mean, to overcome that, and that is basically to go into the field of having software-defined radios. And that means when we could spend a lot of money, basically get lots of capabilities. However, sometimes if you spend more money, I mean, of course, I mean, you get a more powerful software-defined radio with which you can actually control all the pieces. Yeah? However, it takes a lot of time. Yeah, it needs a huge effort basically to get all the pieces together. And on the other hand, I mean, we have all these ASICs, I mean, which give us a much higher performance. Yeah, so there's this kind of trade-off. But in the long run, what we actually need is something which gives us performance so that we can actually bring that into the field, so that we have basically the masses of devices there. But that kind of limits here, or let's say it that way, the openness is basically limited by the big vendors, yeah? And today it's basically the big companies that dictate the openness. Yeah? So when we look at, for example, some huge companies, some hyperscalers, which are trying to basically extend or basically bring the internet also into let's say, high broadband access into the rural areas, they can basically dictate how open this hardware should be. So they can actually put a pressure on the companies. But as a research institutions, we don't have that power. So what we clearly see is, depending on the openness, the research institutions are often left back. Yeah, so they can't really do the groundbreaking research in that field because they are just stuck with this kind of closed system. So what we have to do is we have to convince, or we have to make sure that the future systems are basically much more open than today.
And starting from the challenges, what are the potentials that we look into? So Julius and me, we research into the field of what can we do with joint Wi-Fi resource allocation. So the rate and power control of your Wi-Fi router has a huge potential. We can significantly increase the sum throughput in our Wi-Fi networks that we have around just by increasing the spatial reuse opportunities that we have. We look also into questions like client handovers between different networks, between different Wi-Fi networks, between 3G, 4G, 5G networks and Wi-Fi. And that can be done in terms of seamless, so in a short time scale. And that can be done with all that necessary encryption, authorization, and authentication. And those two worlds from provider networks and decentralized Wi-Fi networks are coming together on that point. And the third field we are interested in is the actually, let's say, all over IP converged kind of Wi-Fi networks and ISP networks for using both passes or using different passes on Wi-Fi networks more efficiently. And also the, let's say, hardest question here, how to manage a decentralized network is quite a tough one. And there are a lot of open questions on how we can solve that.
Yeah, and obviously, I mean, there are more challenges. I mean, what we clearly see is like a trend towards higher frequencies. So in order to achieve more bandwidth, more throughput, but there are also challenges like the resource allocation tasks. I mean, when we basically have a set of different transmission rates, the question is, so how to select like the optimal transmission rate from this set of rates. On the other hand, it's also about like selecting different orthogonal channels in the frequency domain. Like how do you basically create like the base set of carrier frequencies and so on. And we also see if we go, I mean, when we look into future networks, obviously we will have networks which consist of smaller cells, so we will see much more handovers, and we will also see lots of handovers, like vertical handovers between different technologies. But what we also see is, and that is clearly something that we've seen over the last 20 years, that often the authentication and authorization and also the encryption that was used at some point, well, there were impairment, or let's say there were issues on that side. So there's lots of research in the direction also to obtain and do a key derivation from the physical layer characteristics. And that is of a huge opportunity because that can be really guessed by others. Yeah? So, and obviously we also need to make these networks more programmable. Yeah?
The setup that we are working in starts typically on the left lower corner. We take the current hardware, put that in the box and have it installed from the desk on some indoor nodes and then essentially on an outdoor node. And experimentation is like setup experiment, design experiment, merge, traces. That is the playground we use in our systems Wi-Fi research. On the upper right, there's our test bed at the TU Berlin's campus with about 40 to 50 nodes. On the lower right, there is the community network where I'm the technical leader of, the Ethernet EG. It's like an wireless multi-hop network in a rural area here in Thüringen, where people use Wi-Fi mesh networks as their broadband access. So to design hardware, software, and different architectures, protocols, we quickly move to those real systems. And let's say the most complicated setup is like the one where we do measurements in a productive network, which has the advantage to validate your new design against real internet user traffic that is more or less impossible to simulate. But to come to that point, to run a measurement on a productive network, that's quite a tough task.
Yeah, and since we're running out of time, I would keep it rather short. Yeah, I mean, so one current research project that we are working on is basically to apply all of these, or let's say a couple of the challenges that we've heard into these real production, or let's say semi-production networks. And thing that we are looking at is basically AI ML-based multi-armed bandit algorithms for resource allocation to optimize resource allocation in Wi-Fi networks. Also about like cross-layer designs. I mean, how much access do you need from the lower layers? How much information should be passed over the layers? And also they make it more programmable, and also to do the evaluation of these algorithms in the real world. And I think now we are coming to the things what we see in this scope here. And Thomas?
Yeah, to bridge over to the research and development questions for these entanglement-assisted quantum communication. So thanks to Janis to get me in that topic, and I'm still not an expert on this, but the questions that rises, the simple question that rises from our systems perspective are those that we would like to discuss with you afterwards. So if we look at these possibilities for entanglement-assisted quantum communication, it looks at the first glance like a short time boost for bits per second. So obviously, as a networking guy, you think on, okay, can I compensate microbursts on my internet traffic using that technology? Or can I cache some content at peak times while I use off times to distribute entangled quantums? And how does the queue look like if I have a quantum entangled queue and a data queue? So from our perspective, it boils a bit down to the question that we would like to get some answers from you in terms of what is the achievable storage duration right now for those entanglement states? So on practical systems, is there a limit to certain generation and transmission of those entanglement states? What kind of synchronization do we need? And is it limited to fiber versus free space? So that is like most of our interest to, let's say, ask you as the experts on that quantum community. And we are happy to discuss this.
Yeah, so our main interest is obviously, I mean, and this is from the discussions that we had in the past with Janis and also others. Basically, at the HHI, we also, I mean, there are other departments also looking at basically quantum communication, and obviously the goal is how to basically combine that into like testbeds, how to combine that also with like the wireless access. I mean, what we've seen is basically all of the access is moving towards wireless. So the question is, how can the wireless part benefit here, from the entanglement-assisted quantum communication? And the other thing is, I mean, what we've obviously seen is that the hardware is pretty expensive. So the question is, I mean, how can we create a testbed so that others can also leverage it, so that others can build on top of that others can use it, so to have basically a joint platform that we can all basically use in common.
And what we have to offer is that let's say, as Wi-Fi system guys, we are well equipped with how to design good APIs to allocate resources in the Wi-Fi world, but we guess that is also needed in the entangled quantum communication world, and also about communication protocols. So, and how to, let's say, integrate that in a real operating system. Typically, we are using Linux open source implementations, and we are, highly interested in getting our hands to some real quantum entangled piece of hardware, piece of testbed that we could somehow integrate with the testbed and experimentation experience we do have. So, thank you.